Okay, well, let's see here. Now, I wanted to start out by trying a problem, by taking a look at 18.28. I'm sure that all of you have been practicing over the weekend and getting better and better at all the different reactions that we learned in sections 18.1 through 18.11. But before we do that, I want to begin the lecture by backing up and looking at the synthesis strategies and where it says other limitations, because these are things that students tend to forget sometimes. And I just want to reiterate that these are important, okay? These two limitations are very important. So it says here, other limitations that have to be considered when you're planning a synthesis. We spent a lot of time on Monday, last Monday, or yeah, last Wednesday, sorry. On September 30th, we spent a lot of time talking about nitration, okay? We spent all this time talking about nitration and how you do a nitration using nitric acid and sulfuric acid, and you make a nitronium. Well, there's a limitation to nitration. It says here that you can't do nitration on a ring that already contains an amino group. So what's going to happen is if you were to take that aniline and if you were to treat that with HNO3 and sulfuric acid, it's not going to work because it's going to oxidize the amino group. Now, if you're wondering, well, what's it going to oxidize it to? It doesn't look like it's oxidized here. It's going to oxidize it to some kind of, I'm not sure if it's a nitroso something that we haven't learned because he doesn't cover it exactly. But the important thing that you know is that the reaction won't work, okay? My guess is that you'd get a mixture of products and you just see a bunch of different things on TLC. So you wouldn't be any further ahead. But that's a limitation that you've got to be aware of, okay? So no nitration on a ring with an amino group because that amino group will get oxidized. The second limitation is even more of a limitation because there's more scenarios, and that is that you can't do a Friedel-Crafts reaction, cannot do a Friedel-Crafts reaction on a ring that is either moderately deactivated or strongly deactivated, and that's why you've got to be on top of your activating groups and your deactivating groups. So we have weak deactivators, moderate, and strong deactivators, and if we have either a moderate or a strong deactivator, we're going to get no reaction. And again, that will be important. Okay, so I don't want you to just say, oh, that's just something we learned at the end of a lecture. Can't be important. No, those two exceptions are important. The good news is there's only those two that we really have to be concerned about. And with those in mind, this is where I kind of wanted to start as a class this morning, is by looking at 18.28a. So let's just focus on one problem for now. And once we solve this problem, we'll get into the rest of the material in the chapter. But you can see here that on this molecule, rather, we have some groups here. We've got a halogen. We know that halogens are weak deactivators, and they are. We have this isopropyl group, right? Alkyl groups. We know that those are weak activators. They're ortho-para-directing. And then we have this acyl group here. So we have an acyl group. And we know that acyl groups are moderate deactivators, and they are meta-directors. So you can think, well, if I had the isopropyl group and the acyl group installed, right, they're both going to direct to this position, and I can do my bromination using bromine and iron 3 bromide. Sure, no problem. You could do that. But then the question becomes, okay, well, what order am I going to add that isopropyl and that acyl group in? Remember that if we were to try to add the acyl group first, the problem with that, and if you're like, what's the acyl group? I mean, if we were to try to add this group first, okay, which we can do that, you can add an acyl group to a benzene ring, is that that's going to be meta-directing, okay? So that's not going to direct the isopropyl group to the correct position. Whereas if we flip it around, and if we install the isopropyl group first, that is ortho-para-directing, and it's so sterically hindered that it's going to direct the acyl group to that position. Okay, so that's kind of the rationale you want to take here. And with that in mind, let's start our synthesis. We're going to start with benzene as our starting material. And the first thing we're going to do is we're going to install that isopropyl group. This is a Friedel-Crafts reaction. Since we're reacting it with isopropyl chloride and aluminum chloride, we don't have to worry about any rearrangements. And we're going to end up with that isopropyl group on the ring. And I've told you several times throughout this chapter that the name of this, or the common name of this compound, is not isopropyl benzene, it's cumene. It's got its own name like Cher or Madonna. Anyhow, so now we've got that isopropyl group installed. Now we can think about installing that acyl group. Okay, and for that, we're going to use Friedel-Crafts acylation. So we're going to need this molecule, which is called acetyl chloride. I worked with a guy who used to throw it in the sink to scare us. Anyhow, because it makes a popping sound. Anyhow, there we go. So we'll draw our aromatic ring. Now we've got our isopropyl group, which is an orthopara director. We've got our acyl group, which is a meta-director. So both of those groups are going to direct to this position. Now, if you're like, well, what about this position, Mr. Dion? I would say 6 of one, half a dozen of the other. The same thing. They mean the same thing. And so now we can install our bromine, and for that we're going to use bromine, and we're going to use either FeBr3 or we could use AlBr3. Either way, we're going to end up with this molecule. Okay, so there we go with our bromine in the correct position. Here's our isopropyl, and there's our acyl group, like that. Okay, so overall, it's a 1, 2, 3 step process. I want you to remember that this is Friedel-Crafts alkylation. I want you to remember that this is Friedel-Crafts acylation. Okay, and then the last step is bromination. You know what? We got time. Let's take. You know what? Maybe we should move on. Let's finish the chapter, and then if we have time at the end, we'll come back and you can remind me. We'll tackle 18.2b. All right. Okay. Well, let's start something new. Monday morning, brand new day. Let's take a look at the last few reactions that you need to learn in this chapter. And the first one is nucleophilic aromatic substitution. And if you're wondering, hey, isn't that what we've been learning? No, we've been learning electrophilic aromatic substitution, right? Somebody has their mic on. If you could mute it, that would be fantastic. Again, what we've been looking at thus far with this nitration, halogenation, sulfonation, Friedel-Crafts reactions, right? All these different reactions, these were reactions where the aromatic ring behaved as a nucleophile. Now we're going to be looking at reactions where the aromatic ring behaves as an electrophile. Okay, so it's going to be attacked by a nucleophile. Can you all see my screen still? This is 18.13. Okay, good. All right, so again, where was I? It's a reaction where benzene is going to be attacked by a nucleophile. So it says here, if we take para-bromonitrobenzene and we treat that with sodium hydroxide at 70 degrees Celsius, and then we follow that up by a workup with acid, we end up with this para-nitrophenol. And what's happening here is that the hydroxide is acting as a nucleophile, right? Hydroxide is a good nucleophile, it's a strong nucleophile. And the bromide, or the bromine, is acting as a leaving group as bromide. Anyhow, you might be wondering, this is kind of interesting. What would the mechanism of this look like? Well, let's take a look at that. Right? But in order for us to rationalize what's going on in this mechanism, we have to take a look at the requirements for this type of reaction. So this nucleophilic aromatic substitution is called an SNAR reaction. I always think of these fondly because the first job that I ever had when I immigrated to America, working in a lab doing synthesis, the first thing they asked me, they said, "Can you do an SNAR?" I said, "Boy, howdy, can I?" The first thing they asked me to do. Anyhow, what do we have? What requirements do we need for an SNAR reaction? Okay, first of all, the ring has to possess a strong electron withdrawing group. Now, normally it's a nitro group. I'll just say here for this class, we'll put here usually we'll just put NO2 like that. Usually a nitro group. Okay, and this question does come up on the ACS final. I've seen SNAR come up on it almost every time, and they always have a nitro group in the ring, so no stress there. Okay, it's always going to be a nitro. The ring has to possess a good leaving group, a halide, right? Either an iodide, a bromide, or a chloride. Okay, so it's going to have one of those. Now here's the kicker: is that leaving group has to be positioned either ortho or para to the withdrawing group. This is another one. You know what? Mr. Dion doesn't have the ACS funnel memorized, but he's seen enough of it that he's got some questions memorized. And I remember a couple of years ago, we gave the same final, a few different semesters in a row, and it had the leaving group positioned ortho to the nitro group. And so I think they were trying to get students to remember that it's not just para, because usually the examples that they show in the book have it para, but they said, remember, it can be ortho too. Okay, anyhow, and what else is really interesting is that if you try that same reaction that we just saw 2 slides ago, if you try that with the nitro group meta to the leaving group, or meta to the halogen, you get no reaction. So again, it's got to be ortho or para. We could even reiterate that, okay? We could circle this and say must be ortho or para for SNAR to occur. Gotta be ortho or para. And do you guys remember the sigma complex or the rhenium ion that we looked at last week? Well, you're probably wondering, well, if the ring's not behaving as a nucleophile, there isn't going to be a positive charge. Okay, if it's getting attacked by a nucleophile, there's going to be a negative charge. Yeah, there is. Okay, and when we have that negative charge delocalized throughout the ring after the nucleophilic attack occurs, we call that the Meisenheimer Complex. Okay, very cool name, the Meisenheimer Complex. So let's take a look at what the Meisenheimer Complex looks like, drawn out here in gory detail. So what happens in the first step is that you get nucleophilic attack. Let's follow along. Okay, so we get nucleophilic attack by the hydroxide, which is a strong nucleophile right here. Now, this isn't just a 2-step mechanism where you get nucleophilic attack and then you can just draw the loss of leaving group like that. I suppose you could, but that doesn't show the Meisenheimer complex. So we have this arrow here, and then we have a negative charge in our ring, and we can draw that negative charge delocalized throughout the ring. Take a look. The first one, the second one, and the third one. But what else? Why does that nitro group have to be ortho or para? Because we can also draw that negative charge down on the oxygen of the nitro group as well. Okay, and that is what serves to further stabilize that Meisenheimer complex. And then, so basically the way the book describes it is he says, well, the nitro group can be a reservoir for the for that negative charge or for those electrons, and then it, we can push all these arrows shown here at the end to eject the chloride, and then we restore aromaticity. Okay, this is a mechanism you have to know. Okay, know this mechanism, and I guarantee you that I assigned some questions in the book that ask you to draw mechanism of the nucleophilic attack, the Meisenheimer complex. Now, you might be thinking, okay, well, I'm making a phenol derivative in the end, right? Didn't you tell me way back in organic chemistry 1, Mr. Dion, that the pK of a phenol was around 10? And if we have an electron withdrawing group para to it, it's going to be even lower. It's going to be more acidic than that. So if I'm in sodium hydroxide, wouldn't I just deprotonate that? Well, if you were thinking that way, you're a very astute student, and you are correct. Okay, so it says here the substituted phenol product is deprotonated under the hydroxide conditions because it's acidic enough, and so you need to have a second step to get the phenol. You'd have to just treat it with aqueous acid, okay, to neutralize all that base and to protonate the phenoxide. So overall, what's happening if you were to go from here to here, you put step 1 would be excess sodium hydroxide, 70 degrees Celsius. And then in step 2, you would say H3O plus, like that. And the reason I do that is because usually my students don't draw every charged intermediate along the way, and I'm totally fine with that. Absolutely. And the solutions manual doesn't do it either. Sometimes I do, just for kicks, But anyhow, let's take a look at a question where we would apply our newfound SNAR chemistry. It says predict the product of the following reaction. Well, do we meet all of the criteria here? We have a strong electron withdrawing group. Okay, it's a nitro group, and I told you that's what we're going to have almost all the time. Okay, we've got two halogens, right? Those are both good leaving groups. You know, when we just think about leaving groups, generally speaking. But in order for an SNAR reaction to occur, only one of these is going to act as a leaving group. Could anybody tell me which one it would be, the chlorine or the bromine? And it's not a trick question. This would be unlike trick questions. Absolutely, you're both correct. Yeah, Francisca and Andrew, they both say it's the chlorine. Why? Because the chlorine is para to the electron withdrawing group. Remember, that was one of the requirements. Now, there's another requirement, and that's that we have a strong nucleophile. You guys know that methoxide is a strong nucleophile. Okay. Now, nucleophile. Now, of course, the answer to this question is just the SNAR mechanism, right? And you know that you're going to lose this leaving group because all of the criteria are met. And so you could just draw, you know, in fact, in my notes, that's all I have written here. Is nothing more than this, which is correct. You know, it's not wrong. And that's all they're asking for. So if you wrote that down as your answer while you're listening to me talk or something, you said, oh, I can just solve this problem pretty quickly. There you go. That's the answer. No problem. No problem at all. In fact, that's perfect. But I want you to be able to draw this mechanism. So let's get a little practice on it here. And let's start by drawing our methoxide. Put in all of our lone pairs. And let's start by drawing the nucleophilic attack, right? On the aromatic ring. Maybe I'll use a different color arrow here just to highlight it. Oops. There we go. So let's draw something like this, okay? Like that. And let's draw what the intermediate would look like, okay? You know what, maybe I'll turn the ring on its side here because I know I'm going to run out of space. So it will look something like this, where I have my chlorine, my bromine, I have my nitro group down here, like this. There we go. It'll look something like this, and then I have my methoxy here. Okay, so this is my Meisenheimer complex, right? And you should be able to draw, you know, you should be able to draw the delocalization of those electrons, push them around the ring like this, okay? So now I'm going to have lone pair here. I'll drop my nitro off to the side like that. And I've got my methoxy here, my chlorine, okay? So on and so forth, okay? You should be able to draw in this intermediate like that. Okay. Go. Negative charge here. We still have our methoxy and our chlorine, but you know what we haven't done yet? We haven't shown the negative charge being delocalized down into the nitro group. So you should be able to draw that too. So if we curve our arrows like this, like this and like this. Now let's draw the last resonance structure that shows that negative charge down on the nitro. Okay, this is one of my favorite. I say this about everything in chemistry I know. This is one of my favorite mechanisms ever. Is anybody here a fan of wrestling? You know, wrestling? What do you guys call it down here in the States? Is anybody a fan of like WWF, or I guess that doesn't exist? WWE, does that exist? Anyhow, has anybody ever seen the moves in wrestling? You know, throw the guy against the ropes and then he bounces back and does a clothesline to the other guy. This isn't organic chemistry talk, but I always think of that. Eric says, LOL, yep, okay. Right, real classic move in wrestling. Eric, it's what I think about every time I see this. I'll draw it in blue arrows, right? Because you think about it, this negative charge bounced all the way down here, you know, I should put it on the other one right here. It bounced all the way down to the back, and now it's going to ricochet. Woo! It's going to make that chlorine fly out. Even with that sound effect, you know, you do the reaction, you'll hear that. Woo! Okay? Anyhow, I know I'm kind of being facetious here, but there we go. So look at this: 1, 2, 3, blingy, like that, and you nail the whole thing, right? So you lose minus. Anyhow, now I'll think of WWE during the quiz. Well, I guess you could think of worse things during the quiz. Anyhow, give me a thumbs up if you follow me on the Meisenheimer Complex, and if you think that mechanism is pretty interesting, where the nitro can take on that negative charge and then just eject how it ejects that chloride. You don't have to give me a thumbs up that you think it's cool, but just a thumbs up if you understand what the heck is going on. All right, thanks, Sarah. Okay, good. All right, a couple people follow me. That's good. SNAR, I'll be honest with you, on the ACS final, the only thing I've ever seen is this, okay? I've never seen them ask, I don't think I've ever seen them ask anything about a Meisenheimer complex, but I could be wrong. I've been wrong before. Okay, let's take a look at another question here. This is 18.31 from our textbook. It says, starting with benzene and using any other necessary reagents of your choice, design a synthesis of the following compound. So we've got this para-amino phenol, and we want to make this compound. And if you think about it, there's not a lot of ways that we could make this compound, okay? Not a lot of ways that we could do that. I'm even trying to think of alternatives to what's the solution in the solutions manual. Anyhow, I think that this is probably a good time for us to use SNAR chemistry, right? Because we haven't learned any way to install a phenol on a ring, right? We have no option for doing that based on what I've taught you so far in this class, unless we were to have this compound. Okay, if we had a nitro here and we had a good leaving group, we can put a chlorine, we could put a bromine. I don't care what you put. Let's put a bromine just to be cheeky. Okay, you've got to have that compound, and then we could use that to do an SNAR. So SNAR, and I'm just putting that in there to remind you of the mechanism since we're just learning it right now. And then you would treat that with, sodium hydroxide. You beat the crap out of it. You heat it up, I guess. And then you could do the SNAR. So then the question becomes, well, how do I make this molecule? I've got a bromine and I've got a nitro. Well, I would have to install the bromine first, right? Because a bromine is ortho-para-directing and a nitro is meta-directing. It's also deactivating. Okay, so let's install the bromine first. And again, if you drew a chlorine, if you tried this one this weekend and you said, I drew a chlorine, that's fine. No problem. That will totally work. So let's get started here. The first thing we're going to want to do is we're going to want to perform a chlorination on benzene. And in order to do that, we'll use chlorine. You could use AlCl3. You can use FeCl3. Either one will work. Oops. Did I say chlorine when I was talking about bromination? So let me switch that up here. Let's do bromination. This Dion's having a hard time being consistent this morning. There we go. Iron-free bromide. All right, there we go. So now we've got our bromine installed, like that. Okay, the next thing we want to do is we want to install our nitro group. And in order to do that, we're going to use nitric acid, which is very strong acid, sulfuric acid, and even stronger acid. Okay, dangerous acids. You want to make sure you have your PPE on. Gloves, of course. I've been burned by nitric acid several times. It really hurts. Do not recommend it. Okay. Sulfuric acid, not nearly as bad for burns anyway. There we go. Okay, so now we're set up for our SNAR reaction. What do we have to do? We're going to have to treat this molecule with step one. You know what? Let me draw both steps just to show you. Okay, the first step is to treat it with sodium hydroxide. And what did it say? Heat it up to around 70 degrees Celsius, something like that. Okay. What you would get from this reaction, if you, and we looked at this a couple of slides ago, is that you would have your nitro group, but then you would have a phenoxide. Right? You'd end up with this, okay, because the phenol is going to be deprotonated by all the base that you have. So then in the second step, you treat that with H3O+. Okay, and that's going to get you this compound. Oh, I'm going to run this space, aren't I? All right, like that. That gives you phenol, but you've got a nitro and you want to reduce that to an amine. Mr. Dion is running at the space. Okay, so the first step is going to be iron, HCl, and we'll heat that up. Okay, it's not necessary to heat that up, but anyhow, and then in the next step, we'll treat that with sodium hydroxide, deprotonate the aniline, and then we'll end up with the product. Let me just write product like that. Okay, give me a thumbs up if you follow me on that synthesis. So, anybody with me on that one? On a Monday? All right, great, excellent, good. Not simple chemistry. You know, it really isn't. This is where you really have to start having a mental decision tree. And I know that you've all been doing that. Of course, you're got this far in the class. You can't get this far in organic chemistry without learning how to make decisions. But yeah, a lot of decisions to make here. Okay, so practice really makes perfect. Well, that brings us to the last section of new chemistry in this chapter, which is 18.14, because 18.15 just discussed, identifying mechanisms. So this is the last new reaction that you'll learn in chapter 18. It says here, recall an SNAR reaction will not occur if the ring doesn't have a strong electron withdrawing group, right? We've got to have a group like a nitro group, okay? So if you don't have a nitro group, you don't get SNAR reaction. So if you take chlorobenzene, you treat that with sodium hydroxide, and you heat it up, you get nothing happen. Now, this is a reaction that was discovered some time ago. If you really crank the temperature up 350 degrees Celsius, that's very, very hot in organic chemistry. In organic chemistry, we think about heating things up to, well, usually below 150. I mean, 350 is crazy heat for OChem. Okay, but if you do it, you will get some substitution. You might think, well, hey, it's just an SNAR without a nitro. Well, in fact, it's not an SNAR reaction. It's something completely different. And there's been studies that have proven that, okay? So if you use an even stronger base, like sodium amide, you guys remember this base? Remember from the alkynes chapter? We use this all the time. This is sodium amide in liquid ammonia. You don't even have to use high temperature, and you can take chlorobenzene and convert it into aniline. And you might think, well, it's just an SNAR reaction. But hold on, here's where it gets interesting. It says here that the regiochemical outcome proves that this reaction does not proceed through an SNAR mechanism, because if it did, if you just took the amide, ion, NH2 minus, if this was a possibility, okay, you would only end up with this product. And so that cannot happen. In fact, let me delete it. Okay, so the fact that you end up with these two isomers, para-methyl-aniline and meta-methyl-aniline, proves again that this does not proceed through an SNAR mechanism. And if you're wondering, well, what kind of mechanism is going on here? Okay, what kind of mechanism is going on here? Well, let's take a look. And I highlighted that proton for a reason, because if you use an isotopically labeled chlorobenzene molecule, and if you are wondering, what does that mean exactly? It means that this carbon that has the star by it, that's a carbon-14 atom. So we can follow that isotope, and we call this a radio-labeled or isotopically labeled substrate anyhow. And if you do the reaction, you can see that now our carbon-14 is not only here, but it's here. And so that suggests mechanism is the result of what's called Benzyne Formation. You guys all know what benzene is, of course. Ready for a new molecule? New molecule of the day, benzyne. You're thinking, what? A triple bond? I thought, Mr. Dion, I thought you taught me that when you have carbons that are sp hybridized, right, that you'd have to have a linear geometry. Well, let's wait and see the whole story here before we make any harsh judgments. And here's the mechanism of the formation of the benzyne intermediate. You have a proton transfer followed by loss of leaving group. All right, we have the amide ion removing a proton in our proton transfer, and then we have the chloride leaving in our loss of leaving group. And then you can imagine that both of these carbons are going to be susceptible to nucleophilic attack by the amide ion. And if you're like, well, what does that mean? All I mean is this. Right now you have an amide, and that amide, it could attack at this carbon, or it could attack at this carbon. And that's why we end up with a mixture of products. Okay, well, let's move on from there and take a look at what's going on in this mechanism. So those two possibilities for nucleophilic attack are shown here in A and B. The first one shows the amide attacking the radiolabeled, or the isotopically labeled carbon, I should say. And the next one, it shows it attacking the other carbon in that triple bond. So nucleophilic attack by amide can take place at either carbon of benzyne, followed by protonation of the other. So again, first step is a nucleophilic attack. Second step is a proton transfer, just like that. And we give this mechanism a sassy name. We call it elimination addition. In fact, that's the title of this section of the chapter. 18.14 is elimination addition. Why? Because what's happening in the first step, let me go back here, is that, where the heck was I? This part here is, where's my blue pen? I use the green pen. This is an elimination. All right, you're eliminating the chlorine and making a new pi bond, so to speak. I'll talk about that more later on. And then you're adding something to it, right? So this is the addition step, okay? So this is addition, elimination, and addition. And during the elimination, or after the elimination is complete, I should say, you form benzyne as an intermediate. So benzene and benzyne. Okay, let's take a look at the entire mechanism that's put forth on this slide right here. So we have our X, which is probably going to be a chlorine or a bromine, a good leaving group. We have the hydroxide functioning as a base. It's going to pull off a proton from the aromatic ring. So hydroxide functions as a base, deprotonates the aromatic ring. Then the leaving group is ejected. We form benzyne, and then the nucleophile. Here they have it drawn attacking this carbon. If they had drawn it attacking this carbon, that would have been totally fine. Either way, and then we have a proton transfer at the end. There we go. So that's the last reaction, is elimination addition. A little more about that, though. If you're, wondering, what's the evidence that this benzyne is formed? Because you can imagine that benzyne would not be a very stable molecule on account of the way that it's drawn here, right? It looks like these are just plain old sp hybridized carbons, and those are supposed to have a linear geometry. Well, the book goes into a tiny, tiny bit of detail about this. And one of the evidences of benzyne being an intermediate come from this trapping experiment. You might remember the Diels-Alder reaction and furan, which is a diene that is locked in the S-cis conformation. It can react with benzyne to form this cycloadduct, and it's nothing more than just saying it reacts in a Diels-Alder, okay? So that suggests that, yeah, there's a pi bond there, because we had to have some kind of dienophile when we did a Diels-Alder reaction. So that's one little piece of evidence. Okay, and that's going to be enough for our class. The book goes into a little bit more detail, but I'm not going to ask you, write me an essay about the benzyne molecule or anything like that. That would be more of an FYI thing for you. All right, where it discusses that it's kind of like two radicals. Anyhow, again, I won't be quizzing you about that. Okay, let's take a look at a question that involves elimination addition. It says, draw both products that are obtained when 4-chloro-2-methyltoluene is treated with sodium amide followed by treatment with acid. So first, let's start by drawing this big, interesting molecule, 4-chloro-2-methyltoluene. Let's think about it. If I draw toluene, okay, if I just draw, right, methylbenzene, like that, that's a toluene molecule, so toluene. And then, of course, the carbon that has that methyl group on it, that's carbon number 1. So I'll put that down here, and we can label that as carbon number 1. And then if I have 2, 3, 4, like this, on carbon 2, I'm going to put a methyl group. So I have a methyl group here, and then on carbon 4, I have a chlorine. So let's put the chlorine here. So here's our starting material. And what we're going to do is we're going to treat this in the first step. We're going to treat this with sodium amide. And remember that sodium amide, we keep that in liquid ammonia. So that's our first step. Now what's going to happen is that sodium amide, if I draw the amide anion, is a very strong base. Okay. And that is going to form the benzyne molecule. Okay, so we're going to end up forming the benzyne molecule. Now, in the book, I think that he's drawn it. I'm going to draw it the way that he does. So he, says we'll remove this proton right here. Okay, and then we're going to end up with this intermediate where we have our triple bond right here, like this. And like this, and like this, and then we've got our two methyl groups like that. So that's after the deprotonation, right? And we can draw the mechanism for that. We could draw it as a two-step process like that if we wanted to. Okay, the book doesn't draw it that way. He draws it as a deprotonation followed by a loss of Levy group. I'm just trying to help us get through this a little bit quicker. And then, of course, the amide can attack either one of those carbons in the benzyne. It could attack here, or it can attack here like that, okay? Either way, maybe I should put an arrow in green and then maybe an arrow in red, like that. And then we're going to treat that with acid after that. So let me draw the intermediates. I think is the best way to do this. So let's draw the intermediate from the green arrow, and that would look like this. We have our two methyl groups. We have our H2, and then we're going to have our lone pair here, like that. Oops, I'm missing my double bond here. Okay, and then we're going to have this molecule. We have something that looks like this. Yep, good. Sorry, I'm running out of space again. Like that. And then we do the proton transfer after treatment with H3O+. And that's just a quick mechanism, so I'm going to leave that one out. Just transferring a proton from the acid. And that's going to give us these two products. So we're going to end up with this molecule, like that. And then we're going to end up with this molecule, like this. Like that and like that. All right. Sorry, my computer's being really slow here. Piece of junk. So I think, sorry, am I here? Oh, okay. Sorry, my chat is really slow. Is anybody having a lag in their chat? Is it just me? Okay, I'm not getting anything from anybody, so maybe it's just me, or is it just so slow? Maybe just you. Okay, anyhow, maybe it's just me. I'm having a hard time getting my chat to like populate. Okay, anyhow, I can see. So somebody asked, could the amide deprotonate at the 5th position? So what Andrew's asking is, could you deprotonate here? And the answer is yes, you could. So if you were to alternate the bonds, you know, if you drew the bonds, drew them like this, okay, you would end up with this intermediate where you'd have this guy. So you'd have the triple bond here, like that, okay? But if you draw the product of the attack of the amide on this, you're still going to end up with the two same compounds. You're going to end up with this, just more of that compound, okay? So those are the only two products you can form, Andrew. Does that help? All right, if you were to just draw, I don't know if I'm answering your question because I can't see if you're responding or not. Okay, good. Thanks, Andrew. Good. Right, if you were to attack here, you'd end up with this product. And if you were to attack here, you'd still end up with that product, okay? So the way that I drew it, it just shows the formation of both of the products, okay? So there's two possible products. And you know, and I know you guys are all great students, you know, you might be wondering, well, wouldn't you form more of this? I'd say probably, yeah. Yeah, you probably would. Okay, well, that's the last question, or the last bit of new material in this chapter. Let's take a look at the last section, which just deals with identifying the mechanism. Yeah, exactly, Andrew. The question asking for the two products. Yeah, you just have to be able to justify, you know, the two products. That's good enough. Okay, section 18.15. I'll be honest, I've taught this class enough that I found that generally speaking, that students don't struggle a whole lot with identifying the mechanisms, because I find that once they start to memorize them and they look at the reactions enough, they do enough practice, I find that generally speaking, again, my students are very good at identifying when a reaction is electrophilic aromatic substitution. That was what we covered the last two lectures, okay? If it's an SNAR reaction, that's what we just looked at today at the beginning. That was section 18.13, okay? And then 18.14, which deals with elimination addition, okay? If you do struggle with it, so I'm not saying it's impossible. Sometimes maybe students do struggle with it, but you could use this decision tree right here. If your reagent is an electrophile, well, yeah, then it's definitely going to be electrophilic aromatic substitution. If it's a nucleophile and you're set up for an SNAR reaction, then you're going to do an SNAR. And if it's not set up for an SNAR, well, then it's going to have to be an elimination addition reaction. Okay. Now, again, most of what we cover in this entire chapter is electrophilic aromatic substitution. That covers, you know, 90% of what we do in this chapter. Okay. Let's look at, I have one more question in here that deals with benzyne. This one here, it says draw the most likely mechanism for each of the following. There's only one transformation here. This is just, you know, that reaction where you take a molecule like chlorobenzene or bromobenzene that's shown here, you treat it with sodium hydroxide at very high temperature, okay, get a substitution, okay, and this is based off of what? Elimination addition. So let's draw the mechanism. So again, this is elimination addition. That's what's going on here. We'll just draw in this proton. If you want to draw in, you know, this one over here, that's fine too. Okay, I'll just keep it over here. Let's start with the first step, which is going to be our hydroxide. Doing a deprotonation in the loss of leaving group. I'll draw it as a two-step process. So we're going to deprotonate, form our benzyne intermediate. So let's draw the benzyne that we would end up with. Here it is right here. Okay. There's no regioselectivity to worry about because the molecule is perfectly symmetrical. And so now we're going to draw our hydroxide as a nucleophile. So, hydroxide as a nucleophile. And again, it could either attack at this carbon or it could attack at this carbon. It doesn't matter which one you draw it at. You're going to end up with the exact same thing. So let's just go with the red arrow. We're going to get this part, and then we're going to get a lone pair over here. We end up with this intermediate right here. We have our phenol, and then we have a negative charge here. And then in the last step, we're going to treat that with acid. Sorry, we're still in hydroxide, so we're going to protonate that with water. Protonate it like this. Then we end up with our phenol. Okay, I'm still on step one. Okay, still on step one. And think about it. We're in strong base, and phenol has a pK around 10. Right? Water, the conjugate acid of hydroxide, has a pK of 15.7. And so now the hydroxide is going to deprotonate the phenol like this. Okay, so now we end up with the phenoxide. Okay, we end up with our phenoxide. And then in the last step, we're going to protonate using H3O+, right? Using aqueous acid like this. We'll draw the Lewis structure of hydronium. And we're going to draw the protonation. There we go. Boom. And that's going to give us our final product. There we go. Elimination addition. Not the trickiest mechanism in the world, but again, you have to remember that in the first step, since you're in strong base, okay, since you're in a strong base and you're making a phenol, it's going to get deprotonated to make the phenoxide, and then you have to treat it with acid in the end. Okie doke, little acid-base chemistry for you there. All right, next slide is nothing more than a review of the reactions. There are a lot of them. You know, sometimes students, not so much students in organic chemistry, but general chemistry students are always looking for a summary of everything. Well, here's a summary of almost everything that we learned, not everything, but almost everything that we learned in chapter 18. Halogenation, nitration, sulfonation, and desulfonation, right? So the whole concept behind installing a blocking group, we looked at that. We talked about what a sulfonic acid is. Then Friedel-Crafts alkylation, Friedel-Crafts acylation of a nitro. Okay, so nitro reduction. What's another reduction? The Clemmensen reduction. What else? Benzylic oxidation. That was covered in chapter 17, but an important reaction in this chapter nonetheless. What else? Benzylic halogenation or benzylic bromination using NBS. And yeah, that covers just about everything that we've done in this chapter, except for 18.13 and 18.15, or 18.13 and 18.14. Those were covered here. So SNAR chemistry, this is section 18.13, and then elimination addition, that was in section 18.14. Okay, so there's a couple options for the elimination addition. Let's just review them quickly. If you have a good leaving group, but you are using sodium hydroxide, you have to really crank up the temperature to 350 degrees Celsius and then do an aqueous acidic workup. Okay, if you have a better base like sodium amide, the high temperature is not required. And of course, if it boils down to a decision on regioselectivity, you're going to get a mixture of regioisomers. And that is it. I believe that is the last slide in the chapter. Okay. Well, I promised that we would go back to, which question was it? 18.28, I believe. Where was it? 18.28, yes. So I'm just going to write the question on a blank page. And here's some old work that we did as a group. Yeah, I'll just write it out here. And we'll give this one the old college try. Get some good practice in here. This is 18.28b. And the molecule that we want to make is this aniline derivative. So we've got our aniline, we've got our amino group here, we've got our bromine here, and we've got this guy here. We've got a propyl group there. Okay, well, the way that I think about this synthesis is if we want to have this bromine on here, and if we've got an amino group, and we have if we have a propyl group, first of all, that propyl group is going to require some kind of Friedel-Crafts chemistry, right? We have no way of installing an amine except elimination addition, which is not going to be what we use here because we don't use that to make anything this complex. So that tells us that we need to use nitration, okay? So that tells us that at some point that's going to be a nitro group, right? That amino is going to be a nitro that we would reduce to an amine. So let's just think retrosynthetically here. That means that probably we would want to have this intermediate at some point, right? And if you're like, well, how did you get that far, Mr. Dion? Well, this is an ortho-para director, right? That means it'll direct to this position and this position, which is blah. And the nitro is a meta-director, which will also direct to this position. Okay, so that means if we were able to make that molecule that I have drawn in red and to treat that with bromine, all we'd have to do is to treat that with bromine and iron tribromide, and then we would end up with the bromine, and then we would just have to reduce the nitro in the last step. Okay, so then the question becomes, well, how do I make this molecule? And how do I make this, parapropyl nitrobenzene, or whatever you want to call it? Well, I've got an ortho-para director and I've got a meta-director. That tells me that I would want to install this group first, and then I can install the nitro after. If I was to install the nitro first, then I'd be in trouble, right? Because that's a meta-director. Okay, and so let's start by installing that propyl group. There's a lot of things to consider here in this sequence. Let me kind of go over this slowly and just remind you that if we want to add that propyl group, okay, onto a benzene ring, I can't just use, one propyl chloride and aluminum trichloride. Remember that? We talked about that in the very first class of chapter 18. And we said that if you were to do that, you'd actually get a mixture of regioisomers, right? You'd end up with, not regioisomers, you'd end up with a mixture of isomers, sorry. You'd end up with this compound where you have the propyl group like this, plus you'd end up with cumene, right? That carbocation would rearrange. So that doesn't get you any further ahead. And so based off of that, our best option is to do a Friedel-Crafts acylation. So that means we'd want to start with this molecule here, which is called propionyl chloride or propanoyl chloride. Either one is totally fine. And with that, we could make this compound where we have our acyl group like that with 1, 2, 3 carbons. Now this is a moderate deactivator, and this is a meta-director. And we want to put our nitro group here. And so that tells us that we're going to have to reduce that carbonyl using a Clemmensen reduction. And so the Clemmensen reduction, for that we use the zinc mercury amalgam with hydrochloric acid, and we cook that up and we excise that oxygen, and we end up with propyl benzene. Seems kind of complicated. You're like, oh, all I wanted was a propyl group. Well, this is the kind of things you have to do sometimes in organic chemistry. To just install a propyl group is a 2-step process. Okay, but now we're set up that we've got a good ortho-para director. And remember, I told you that when you have any kind of alkyl group that's bigger than a methyl group, the para substitutes because there's free rotation around this carbon-carbon bond, and that's going to cause steric hindrance. And so if we treat that with nitric acid and sulfuric acid to perform a nitration, it's going to occur at the para position. So let's do just that. Let's treat it with nitric acid and sulfuric acid. And now we're going to make this compound. So we have our nitro group where we want it to be. Got our propyl and we've got our nitro like that. Okay, what's next? The next thing is that we're going to install the bromine. And the reason, again, that we're going to do that is because we're perfectly set up to do it. We couldn't be any better. We've got a meta-director here that's going to direct to this position. And we've got an ortho-para director here, and the para position is blocked. So that's going to direct exclusively to this position. So let's write out the conditions for bromination, which are bromine and FeBr3, like that. Clean it up a little bit. And we're going to end up with the bromine installed right here, like this. Okay. And then the last step is just going to be reduction of that nitro. Now remember that reduction is a two-step process. The first step is to treat it with iron or zinc in HCl, heat that up, and then in the second step, we're going to treat that with sodium hydroxide, right? Because you would end up with the anilinium. Okay, and so we would end up with this as our final product, where we end up with an amino group here, our aniline. We have our bromine added to that, and we have our propyl group. How many steps is this sequence? We've got 1, 2, 3, 4, 5, and 6. The total is, this is a 6-step process to synthesize this molecule. Okay, is anybody up for some more practice? Somebody says, could you do the reduction before the addition of the bromine? No, it's not going to work nearly as well, right? Because if you were to do the reduction first, then you've got an ortho para activator, and this is a strong ortho para director, right? Then you would get bromination in this position, because this is an ortho para director, but it's weak, and we always go with the stronger one. So no, the answer would be no. All right, who's up for some practice? Anyone? Okay. Since I'm getting no sign, I'll just assume that we want to try some practice. Okay, are there any questions before we move on? You just want to get to it? Yeah, 15 minutes. We can try some good practice questions. All right, let's give a few a try here. Don't look at the answers. Okay, remember, exhaust your knowledge, look through your notes, because if you look at the answers, if you could learn just by reading a solutions manual, we'd all have we'd get our degrees a lot quicker. Okay, so I want to take this molecule, anisole, and I want to make this molecule. Okay, I want to install a nitro group here, and I want to put a bromine down here. This brings me to my next point, something that I didn't bring up, I don't think, in the last lecture. Let's see if I can find it here in my notes. Make a lot of notes. If you go back in your notes, you don't have to do this because I'm going to explain it to you right now. If you go back to, oh, come on, where is it? Good gravy. Anyhow, while I'm trying to find what page I had this written on, I want you to give this one the old college try. Oh, I know where it was. It's in the section of activating groups. Section 18.7. Yeah, there's a little nuance here that I want to mention to you. And that is, this is something that is kind of sprung on you in the solutions manual. And he doesn't do that a lot, I find. But if you remember on slide 43, I had written, if you take anisole and you treat it with excess bromine, then you end up with polybromination. You put bromines in all the ortho and para positions. Okay, that's when you have an excess of bromine. If you take that same molecule, okay, if you take anisole and you treat it with one equivalent of bromine, or if you just write Br2 like that, you can assume that it's going to brominate in the para position. Okay, you can assume that you'll get this molecule because of the free rotation around here, which will cause steric hindrance at the ortho positions. You kind of have to be aware of that to solve this problem because he only does it in a couple of steps. So based off of that, could anybody tell me what you would want to do first here? Would you do the nitration or would you do the bromination? Darn it. Sorry, my chat's kind of frozen here. Okay, there you go. Okay, so my students are saying bromination. I would buy that, yes. So if we treat this with bromine, remember we don't need a Lewis acid catalyst because this is such a strong activator. Okay, we could even write that here. Strong activator that we end up with our bromine in the para position, like that. Okay, Br2, and then we can simply nitrate that. And again, they're both ortho-para directors, right? This is an ortho-para director, and this is an ortho-para director. But remember, this is strong, okay? And this one is a weak deactivator. Okay, this is a weak deactivator. And so if we treat that with nitration conditions, which are nitric acid and sulfuric acid, it's going to nitrate ortho to the methoxy. Okay, let's try another one. This is 18.63. Let me try something more interesting here. Something a little more complex. Let's do this one. This is 18.63C. There are all kinds of good questions in the textbook. I just like to stick to the synthesis ones because I find there's the most kind of content for my students. You know, they're the most dense of all the problems. A lot of chemistry gets covered in a few synthesis problems. So we want to make this para-nitrobenzoic acid from cumene. And the way I would think about this is that really the only way that we've learned how to make a carboxylic acid, okay, when we have an alkyl group is that we're going to have to treat that with, you know, we're going to have to oxidize that, okay? And then, of course, you have to do an acidic workup with that. But so we're going to have to do a benzylic oxidation, okay? And we're also going to have to install that nitro group. Now, we could do the benzylic oxidation last. There's no problem with that. But how would I install a nitro group here, ortho to this isopropyl group? Does anybody have a strategy that they might employ for this one? Where we might start? Eric, so I typed your answer in the chat. Ah, there we go. So I have 2 students, excellent. 3 students that are saying add a blocking group. Couldn't agree more. And so if you're like, what are these students saying? Well, if we were to treat this with fuming sulfuric acid, what are we going to get? We're going to end up putting a sulfonic acid para to that big old isopropyl group, right? We'll end up with a sulfonic acid here. Now remember, this is an ortho-para director. This is a meta-director. Hey, we're going to be set up perfectly to do our nitration in this position. So let's do that. Okay, let's delete some of this spinach. Okay, and then we're going to draw an arrow like this. Nitration is simply nitric acid and sulfuric acid, like that. And we'll end up with this molecule where we have our nitro group here, and we have our sulfonic acid here. Does anybody remember the conditions to remove the sulfonic acid? I'm sure somebody does. I'll just see if anybody can help me. Does anybody remember the conditions to remove that sulfonic acid? Yes, good. All right, perfect. My students are saying treat it with dilute dilute sulfuric acid there should be on, and you are 100% correct. We're going to treat that with dilute sulfuric acid, like that. Now we're going to have this compound. All right, and the next step is just going to be a benzylic oxidation. So the first step is to treat that with KMnO4, water, and that up. Okay, you end up with the carboxylate, and then in the last step, you treat it with hydronium, just like that. All righty, killing it. To try one more, maybe. Let me do that one. Let's try 18.26. Did we do that one?